14 billion years ago, everything that exists today was compressed into a point smaller than an atom, then exploded outward faster than light itself. But what if we have it backwards? What if the Big Bang was not an explosion from nothing, but something far stranger? A white hole spewing matter and energy from another universe entirely. We will journey through colliding dimensions, explore cosmic fountains that defy physics, and uncover evidence that our entire reality might be the exhaust from the universe next door. Prepare yourselves. We begin. We stand at the edge of the greatest mystery in science. The Big Bang Theory tells us that 13.8 billion years ago, all matter and energy emerged from a singularity, a point of infinite density where physics breaks down completely. But here lies the problem that has haunted cosmologists for decades. How does something come from absolutely nothing? The mathematics work perfectly until that first moment. Then they collapse into nonsense. Temperature becomes infinite. Density becomes infinite. Time itself stops having meaning. Think of it like trying to divide by zero on a calculator. The screen just shows error. That is exactly what happens when we try to understand the first instant of our universe. Every equation that describes reality simply cannot handle the conditions at the Big Bang. We can trace the universe back to when it was 1 second old, 1 millisecond old, even 1/1,000,000th of a second old. But that final step to zero remains impossible. Scientists have proposed countless solutions. Maybe time itself began at the Big Bang. Maybe our universe is one bubble in an infinite foam of universes. Maybe quantum fluctuations in empty space created everything we see. But each explanation requires something to already exist: time, space, quantum fields, or physical laws. None truly explains creation from absolute nothingness. The singularity at the Big Bang shares an eerie similarity with another cosmic phenomenon that physicists understand even less. Black holes also contain singularities, points where matter collapses to infinite density and our equations fail. But Einstein's relativity suggests something remarkable. Every black hole might have a mirror image, a white hole that expels matter and energy instead of consuming it. While black holes trap everything behind an event horizon, white holes do the opposite. They explosively reject everything, making it impossible for matter or light to enter. If you could somehow approach a white hole, you would see it blazing with incredible energy, spewing matter outward at tremendous speeds. The resemblance to our universe's birth is impossible to ignore. Consider the evidence. Both the Big Bang and white holes involve massive amounts of matter and energy appearing from a single point. Both create event horizons that separate inside from outside. Both involve singularities where physics breaks down. The Big Bang scattered matter throughout space in all directions, exactly as a white hole would. Even the cosmic microwave background, the leftover heat from the early universe, matches what we would expect from a white hole cooling down over billions of years. But this raises an even more disturbing question. If our Big Bang was actually a white hole, where did all that matter and energy come from? The answer might lie in understanding what happens on the other side of the cosmic mirror. Next, we dive into the strange physics of white holes themselves. White holes exist in the mathematics of general relativity as perfect opposites to black holes. While a black hole is a region where matter falls inward and can never escape, a white hole is a region where matter erupts outward and nothing can ever enter. If you imagine space-time as a rubber sheet, a black hole creates a deep pit that traps everything, while a white hole forms an impossible mountain that launches everything away. Both are solutions to Einstein's field equations, but only one seems to exist in our universe. The physics of white holes defies common sense in ways that make even black holes seem simple. Picture standing at the edge of a white hole's event horizon. Unlike a black hole, where you could cross the boundary and fall inward, a white hole's event horizon acts like an impenetrable barrier. You cannot enter because matter and energy are constantly streaming outward at the speed of light. It would be like trying to swim up a waterfall that flows at infinite speed. From the outside, a white hole would appear as the brightest object imaginable, a blazing sphere that continuously creates matter and energy from nothing. The matter emerges from the central singularity already moving faster than light, then slows down as it crosses the event horizon into normal spacetime. This creates a shell of material that expands outward, carrying enormous amounts of energy. But here is where white holes become truly strange. According to relativity, time flows differently near massive objects. At a black hole's event horizon, time appears to stop for outside observers. At a white hole's event horizon, time would flow backwards. An outside observer watching a white hole would see matter emerging in reverse chronological order. The last particles to leave the singularity would appear first, and the first particles would appear last. This temporal weirdness might explain why we do not see white holes in our current universe. They may only be able to exist at specific moments in cosmic history, when the universe has the right conditions to support such exotic objects. Some physicists argue that white holes are fundamentally unstable. Any small perturbation would cause them to collapse or explode. Others suggest they exist, but are hidden behind event horizons that make them invisible to outside observers. The mathematics reveal something even more remarkable. The interior of a black hole and the interior of a white hole are actually the same region of space-time. They are two different ways of looking at the same underlying geometry. A traveler falling into a black hole would, from their perspective, eventually emerge from a white hole in another region of space-time, possibly another universe entirely. This connection suggests that black holes and white holes always come in pairs, connected by Einstein-Rosen bridges or wormholes. Matter that falls into a black hole in one universe might emerge from a white hole in another. If this is true, then our Big Bang could be the white hole exit of a massive black hole somewhere else. But the evidence goes deeper than mathematics alone. Deep in the equations of general relativity lies a shocking possibility that most physicists prefer to ignore. Every black hole in our universe might be connected to a white hole in another universe through an Einstein-Rosen bridge, a tunnel through spacetime itself. This means that every star that collapses into a black hole, every particle that crosses an event horizon, might not be destroyed at all. Instead, it could be transported to another realm of existence and expelled through a white hole, creating matter and energy in a completely different cosmos. The mathematics work with terrifying precision. When you trace the geometry of a black hole's interior, the equations naturally extend into another region of spacetime. This region has all the properties of a white hole, matter and energy emerging from a central singularity, an event horizon that nothing can cross inward, and a connection to our universe through the black hole's core. The two objects share the same interior spacetime, but have opposite orientations in time. Consider what this means for cosmic evolution. In our universe, massive stars collapse into black holes when they run out of fuel. The matter that falls into these black holes does not simply disappear. It gets funneled through space-time to emerge in another universe. That other universe would see continuous creation of matter and energy, appearing as white holes scattered throughout their cosmos. Meanwhile, if their stars collapse into black holes, the matter would tunnel back to create white holes in our universe. This creates a cosmic recycling system of staggering implications. Matter is never truly created or destroyed. It simply moves between parallel universes through these space-time tunnels. Each universe feeds the other, with black holes serving as exits and white holes serving as entrances. The total amount of matter and energy across all connected universes remains constant, but it can flow freely between them. But here is where the theory becomes deeply unsettling. If this process has been happening throughout cosmic history, then most of the matter in our universe might not have originated here at all. The atoms in your body, the stars in the sky, the planets orbiting distant suns, all of it could be recycled material from civilizations and worlds in other universes. We might be living in a cosmic graveyard, built from the remnants of countless other realities. The implications extend even further. If white holes create matter in our universe, then we should be able to detect them. They would appear as objects that continuously generate energy without any visible source of fuel. They would shine with the light of creation itself, powered by matter falling into black holes in distant universes. Some astronomers have suggested that certain mysterious objects, like quasars, gamma-ray bursts, or even the cosmic microwave background itself, might actually be evidence of white holes operating in our cosmos. The connection becomes even more profound when we consider the Big Bang itself. If our entire universe began as a single massive white hole, then everything we see around us emerged from a black hole in another reality. The evidence for this cosmic connection is hiding in plain sight. The most ancient light in our universe carries a secret message about its violent birth. The cosmic microwave background radiation fills every cubic centimeter of space with the leftover heat from when our universe first became transparent to light. About 380, 0 years after the Big Bang, this radiation appears almost perfectly uniform in all directions, with tiny variations that seeded the formation of galaxies and stars. But hidden within this ancient glow are patterns that suggest something far more extraordinary than a simple explosion from nothing. The temperature of this background radiation is exactly 2.725 Kelvin above absolute zero, cold enough to freeze any known substance solid. This represents the cooled remnant of what was once the hottest plasma imaginable, with temperatures exceeding billions of degrees. As the universe expanded, this plasma stretched and cooled, like the exhaust from a cosmic engine gradually losing its heat. The mathematical signature matches perfectly with what we would expect from a white hole that has been cooling for nearly 14 billion years. But the real evidence lies in the uniformity itself. The cosmic microwave background is so evenly distributed that regions of space separated by billions of light years have exactly the same temperature. This presents what cosmologists call the horizon problem. How did distant regions of the universe coordinate to reach the same temperature when they have never been in contact with each other? Light has not had enough time since the Big Bang to travel between these regions and equalize their temperatures. The standard solution involves cosmic inflation, a period when space itself expanded faster than light, stretching tiny quantum fluctuations into cosmic-sized temperature variations. But this theory requires exotic physics and precise fine-tuning that many scientists find unsatisfying. The white hole hypothesis offers a simpler explanation. All the matter and energy in our universe emerged from the same source, a single white hole connected to a black hole in another universe. If our Big Bang was actually a white hole, then the uniform temperature makes perfect sense. All the matter and energy originated from the same interior region of a black hole, so it naturally started with the same temperature and density. As this material emerged through the white hole, it carried the thermal signature of its origin. The slight variations we observe today would represent the last moments of whatever fell into the parent black hole. Different stars, planets, and civilizations contributing their unique signatures to the mix. Even more intriguingly, the cosmic microwave background contains unexpected patterns called anomalies that do not fit standard Big Bang models. There are mysterious cold spots, preferred directions in the polarization, and correlations across scales that should not exist. These features have puzzled cosmologists for decades, leading some to question whether our universe is truly homogeneous and isotropic as assumed. But if our universe emerged from a white hole, these anomalies might represent the geometry of the parent black hole and the universe that created it. The patterns could be fossils, ancient imprints of the cosmic structure that existed before our reality began. The evidence becomes even stronger when we examine the largest structures in our universe. Something invisible and massive is dragging our galaxy toward it at 600 kilometers per second. The Great Attractor lies hidden behind the dust and stars of our own Milky Way, making it nearly impossible to observe directly. But its gravitational influence is undeniable. It pulls on thousands of galaxies across hundreds of millions of light years, including our own local group. This cosmic traffic jam defies our understanding of how matter should be distributed in a universe that began with the Big Bang. The mystery deepens when we realize that the Great Attractor itself is being pulled towards something even larger and more mysterious. Astronomers have mapped the flow of galaxies across billions of light years and discovered that everything is moving toward a region of space called the Shapley supercluster. But even this massive collection of galaxy clusters cannot account for the observed motion. Something else must be out there. Something so massive that it dominates the gravitational field across significant portions of the observable universe. The standard model of cosmology struggles to explain how such large-scale structure could have formed from the smooth initial conditions of the Big Bang. But if our universe began as a white hole, these mysterious attractors make perfect sense. A white hole would not create matter uniformly in all directions. It would have preferred axes and orientations determined by the geometry of the parent black hole. The matter emerging from different parts of the white hole's event horizon would carry momentum in specific directions, creating large-scale flows that persist for billions of years. Think of it like water emerging from a complex nozzle. The flow pattern depends on the shape and orientation of the nozzle, not just the pressure behind it. Similarly, a white hole would imprint the geometry of its parent black hole onto the matter it creates. If that parent black hole was rotating, had magnetic fields, or was distorted by nearby massive objects, these features would show up as preferred directions and flows in the resulting universe. The Great Attractor and similar structures could be fossil remnants of the original white hole geometry. They represent the grain of our universe, the underlying pattern that was established when everything we see emerged from a single point source. This explains why galaxy flows seem to converge on specific regions, rather than spreading randomly in all directions as the Big Bang model predicts. Recent observations have revealed an even more disturbing possibility. The Great Attractor appears to be part of an enormous structure called the Great Wall, a sheet of galaxies stretching across more than 500 million light-years. This wall is so large that light has not had enough time since the Big Bang to cross it, meaning its different parts should not be gravitationally connected. Yet somehow, this structure exists and influences the motion of matter across vast distances. If our universe is the product of a white hole, then structures like the Great Wall represent the last major features that fell into the parent black hole before our universe began. The implications reach far beyond our cosmic neighborhood. The missing mass that holds our universe together might not be exotic particles at all. Dark matter makes up 85% of all matter in the universe, yet it interacts with ordinary matter only through gravity. It does not emit, absorb, or reflect light, making it invisible to all our telescopes and detectors. Scientists have spent decades searching for dark matter particles in underground laboratories, particle accelerators, and space-based observatories, but every experiment has come up empty. The absence of evidence is becoming increasingly difficult to ignore. But what if dark matter is not made of particles we have never discovered? What if it represents something far stranger, the gravitational influence of matter that exists in the parent universe, connected to our white hole Big Bang? The mathematics of Einstein-Rosen bridges suggest that gravitational fields can leak through the tunnel, connecting a black hole to its white hole counterpart. This means we might be feeling the gravitational pull of objects that exist in another universe entirely. Consider the implications. Every galaxy in our universe appears to be embedded in a massive halo of dark matter that provides the gravitational scaffolding for star formation. These halos have specific shapes and densities that match computer simulations remarkably well. But if dark matter consists of ordinary matter in another universe, then these halos would represent the gravitational shadows of galaxy clusters surrounding the black holes that feed our white hole cosmos. The evidence fits with disturbing precision. Dark matter halos are most massive around the largest galaxies, exactly as we would expect if they represent the gravitational influence of the most massive black holes in the parent universe. The distribution of dark matter throughout our cosmos follows the same large-scale structure as ordinary matter, suggesting they share a common origin. Even the ratio of dark matter to ordinary matter, about 5:1, matches what we might expect from the inefficiency of matter transfer through Einstein-Rosen bridges. This explains why dark matter particles have never been detected, despite decades of searching. They do not exist in our universe at all. They are regular atoms, stars, and planets in another reality whose gravitational fields reach across the dimensional divide. We are literally feeling the weight of another cosmos pressing down on our space-time through the network of wormholes that connect every black hole to its white hole partner. The theory also explains dark matter's strange behavior during galaxy collisions. When two galaxies crash together, their stars and gas interact through electromagnetic forces, but their dark matter halos pass through each other with minimal interaction. This makes perfect sense if dark matter represents gravitational shadows from another universe. The shadows can overlap without affecting each other because they originate from completely separate objects in separate realities. Even more remarkably, this interpretation of dark matter provides a test for the white hole Big Bang hypothesis. If dark matter comes from gravitational leakage through wormholes, then its distribution should correlate with the locations of black holes in our universe. Regions with more black holes should show stronger dark matter signals, and the orientation of dark matter halos should align with the preferred directions established by our universe's white hole origin. The connection between realities runs deeper than gravity alone. The spookiest phenomenon in physics might be proof that our universe shares quantum information with others. Quantum entanglement allows particles to maintain instantaneous connections across any distance. Sharing information faster than light could travel between them. When scientists measure the spin of one entangled particle, its partner immediately adopts the opposite spin, regardless of whether they are separated by meters or millions of light years. Einstein called this spooky action at a distance because it seems to violate the fundamental principle that nothing can travel faster than light. But what if entangled particles are not communicating across space at all? What if they are sharing information through the same Einstein-Rosen bridges that connect black holes to white holes? The mathematics of wormholes suggest that quantum information could flow through these space-time tunnels without violating relativity because the information would not be traveling through normal space. It would be taking a shortcut through higher dimensions. This possibility becomes even more intriguing when we consider the origin of entangled particles in our universe. If our Big Bang was actually a white hole, then every particle that emerged would carry quantum information from whatever fell into the parent black hole. Particles that were entangled in the original universe would remain entangled after passing through the wormhole, creating quantum connections that span the dimensional divide. Think about what this means for the nature of reality. Every quantum measurement in our universe might be influenced by events happening in the parent universe. When we observe a particle's spin or position, we are not just measuring properties that exist independently. We are accessing information that is simultaneously stored in another cosmos. The randomness that appears to govern quantum mechanics might actually reflect the chaotic dynamics of matter falling into black holes in the parent universe. Recent experiments in quantum mechanics have revealed phenomena that support this interpretation. Quantum teleportation allows scientists to transfer the complete quantum state of one particle to another, destroying the original in the process. The information appears to travel instantaneously, but it requires a classical communication channel to complete the transfer. This matches exactly what we would expect if quantum information flows through wormholes, while classical information must travel through normal spacetime. Even more remarkably, some physicists have proposed that the interior of every black hole contains a copy of all the quantum information that ever fell into it, stored on the event horizon in a two-dimensional hologram. If this is true, then the white hole that created our universe would contain a complete quantum record of everything that existed in the parent cosmos. Our entire reality might be a three-dimensional projection of information stored on the surface of a black hole in another universe. This holographic principle explains why entanglement appears to connect particles across vast distances. They are not actually separated. They are both reflections of the same information stored on the event horizon of the parent black hole. When we measure one particle, we are accessing the same quantum record that determines the properties of its entangled partner. The implications extend beyond individual particles to the structure of spacetime itself. Everything you see, touch, and experience might be a projection from the surface of a black hole. The holographic principle suggests that all the information contained within any region of space can be encoded on the boundary of that region, like a three-dimensional image projected from a two-dimensional surface. This radical idea emerged from studying black holes, where physicists discovered that the amount of information a black hole can contain depends on the area of its event horizon, not the volume of its interior. The implications are staggering. Our three-dimensional universe might actually be information stored on a two-dimensional surface. If our Big Bang was a white hole connected to a black hole in another universe, then our entire cosmos could be a holographic projection of information encoded on that black hole's event horizon. Every atom, every star, every galaxy would be a three-dimensional shadow cast by patterns of information on a distant, two-dimensional surface. We would not just be living inside a projection, we would ourselves be part of the projection. Conscious patterns of information experiencing the illusion of three-dimensional existence. The evidence for this interpretation comes from the mathematical structure of general relativity itself. When physicists trace the geometry inside a black hole, they find that all possible paths eventually lead to the same central singularity. But viewed from the outside, an observer watching matter fall into a black hole would see it freeze at the event horizon, its information spread across the surface in a holographic encoding. Both perspectives are equally valid descriptions of the same physical system. This duality extends to our own universe. From our perspective inside the cosmos, we experience three-dimensional space expanding from a Big Bang singularity. But from the perspective of observers in the parent universe, our entire reality might appear as information patterns evolving on the surface of their black hole. The expansion of our universe would correspond to information spreading across the event horizon as more matter falls in from their side. The holographic principle explains several puzzling features of our cosmos. Why does the cosmic microwave background radiation appear to come from a two-dimensional surface surrounding us? Because it represents the projection of information from the black hole's event horizon. Why do the laws of physics seem perfectly calibrated to allow the existence of complex structures like stars, planets, and life? Because they reflect the information processing capabilities of the holographic encoding system. Even more disturbing is what this means for free will and consciousness. If we are holographic projections, then our thoughts, decisions, and experiences might be determined by information patterns evolving on a two-dimensional surface in another universe. Every choice we think we make freely could be the result of quantum fluctuations in the parent black hole's event horizon. Our sense of agency and self-determination might be elaborate illusions created by the holographic projection process. But the holographic principle also offers hope. If information cannot be destroyed, even when it falls into a black hole, then consciousness might be fundamental and indestructible. Death might not be the end, but simply a transition from one form of information encoding to another. The connections between universes may be more intimate than we ever imagined. Every black hole in our universe is slowly evaporating, and when they die, entire universes might die with them. Stephen Hawking discovered that black holes are not completely black. They emit radiation due to quantum effects near their event horizons. This Hawking radiation carries away energy, causing black holes to gradually shrink and eventually evaporate completely. The smaller the black hole, the faster it radiates away its mass. Stellar mass black holes will take longer than the age of the universe to evaporate, but microscopic black holes would disappear in fractions of a second, releasing their entire mass as pure energy. But if black holes are connected to white holes in other universes, what happens when a black hole evaporates? The Einstein-Rosen bridge that connects it to its white hole partner would collapse, severing the link between the two realities. From our perspective, any white holes in our universe, connected to evaporating black holes, would suddenly stop producing matter and energy. They would appear to shut off like cosmic faucets being turned off. The implications are terrifying. If our entire universe emerged from a white hole connected to a black hole in another cosmos, then our reality depends on that parent black hole continuing to exist. Should it ever evaporate completely, the flow of energy that powers our cosmic expansion would cease. Our universe would begin to collapse back on itself, reversing the Big Bang and crushing everything back into a singularity. The timeline for this cosmic death depends on the mass of the parent black hole. If it was formed from a single massive star, it would evaporate in about 1067 years, an unimaginably long time, but still finite. If it was a supermassive black hole like those found at the centers of galaxies, it could survive for 100 years or longer. But eventually, unless the parent black hole continues to grow by consuming new matter, it will shrink to nothing and take our universe with it. This creates a disturbing symbiosis between connected universes. Our universe needs the parent black hole to survive, but that black hole needs matter falling into it from the parent universe to avoid evaporating. If the parent universe goes through its own heat death and stops feeding matter to its black holes, then our universe would be doomed as well. We are living in a cosmic ecosystem where the death of one universe cascades to cause the death of others. But Hawking radiation also offers a glimmer of hope. The radiation emitted by a black hole carries information about everything that ever fell into it. If our universe is connected to a black hole through a white hole, then information about our cosmos might be encoded in the Hawking radiation emanating from the parent black hole. Even if our universe is destroyed when the black hole evaporates, the information that defines our reality would persist as thermal radiation in the parent cosmos. This raises profound questions about the nature of existence and consciousness. If the information that makes us who we are survives in Hawking radiation, are we truly dead when our universe ends? The answer may lie in understanding how black holes form in the first place. Every time a massive star dies in our universe, it might give birth to a new cosmos. When a star, at least 25 times more massive than our sun, runs out of nuclear fuel, gravity overcomes all other forces and crushes the star's core into a black hole in less than a second. The outer layers explode outward in a supernova that briefly outshines an entire galaxy, while the core collapses past the point of no return. What happens next has been hidden behind the event horizon since Einstein first predicted black holes nearly a century ago. But if black holes connect to white holes in other universes, then stellar collapse is not an ending but a beginning. The matter crushed into the black hole does not disappear. It emerges as a Big Bang in another reality. Every supernova in our night sky might mark the birth of trillions of galaxies, countless stars, and potentially countless civilizations in universes we will never see. The death of one massive star could seed an entire cosmos with the building blocks of complexity and life. This transforms our understanding of cosmic evolution. Instead of being a random accident in an indifferent universe, life might be an inevitable consequence of stellar death and rebirth. The heavy elements that make up our bodies, carbon, nitrogen, oxygen, and iron, were forged in the cores of dying stars and scattered by supernovae. If those same elements then seed new universes through black hole formation, life becomes a cosmic inheritance passed from one generation of universes to the next. The process might even be self-reinforcing. Universes that produce many massive stars would create many black holes, spawning many child universes. Those child universes would inherit the physical constants and initial conditions that favor star formation, making them likely to produce their own generations of stellar offspring. Over cosmic time, the multiverse would evolve toward configurations that maximize the production of complexity, structure, and potentially consciousness. But stellar collapse into black holes is not the only way new universes might be born. Theoretical physics suggests that microscopic black holes could form during high-energy particle collisions, either naturally in cosmic ray interactions or artificially in particle accelerators. If these tiny black holes connect to white holes in other realities, then every cosmic ray shower and every high-energy experiment might create miniature universes that expand to cosmic proportions in their own space-time. This possibility has profound implications for our responsibility as an intelligent species. If our scientific experiments can create universes, then we bear moral responsibility for the realities we bring into existence. Every time we collide particles at high energies, we might be playing God with the fate of countless future civilizations. The decisions we make about how to conduct high-energy physics could determine whether child universes develop in ways that support or prohibit the emergence of consciousness. The connection between stellar death and cosmic birth suggests that our universe exists within a vast genealogy of interconnected realities. Each one spawned from the collapsed remnants of massive stars in its parent cosmos. But this raises disturbing questions about our own cosmic ancestry. If our universe was born from a white hole, then somewhere in another reality, a civilization watched their star system get consumed by a black hole. The matter that makes up our entire cosmos, every galaxy, every star, every planet, and every living being might once have existed as a thriving civilization in another universe. Their sun could have been a massive star approaching the end of its life, growing unstable as nuclear fuel ran low in its core. They might have been advanced enough to recognize the signs: increasing stellar output, irregular flares, and the inexorable expansion that signals a star's transition toward supernova. Perhaps they tried to escape. An advanced civilization facing stellar collapse might attempt to evacuate their star system, loading their population onto generation ships bound for distant stars. But if their sun was destined to become a black hole, escape might have been impossible. The gravitational effects would begin long before the final collapse, disrupting planetary orbits and making interstellar travel increasingly difficult. They might have watched helplessly as their world was pulled apart by tidal forces, knowing that their entire reality was about to disappear behind an event horizon. The final moments would have been indescribable, As their planet crossed the black hole's event horizon, time would have slowed to a crawl from the perspective of outside observers. But for the dying civilization, time would continue normally as they fell toward the central singularity. They would experience the ultimate fate of all matter entering a black hole. Spaghettification, where gravitational tidal forces stretch objects into long, thin shapes like spaghetti. But according to the white hole hypothesis, their death was not the end. The information that defined their civilization, the quantum states of every atom in their bodies, the molecular structures of their DNA, the neural patterns that encoded their memories and consciousness, all of it would be preserved and transmitted through the Einstein-Rosen bridge, connecting their black hole to our white hole Big Bang. This means we might be living in the expanded remnants of their reality. The atoms in our bodies could be the same atoms that once formed their bodies. The carbon in our DNA might have once stored their genetic information. The iron in our blood could have flowed through their veins. We would be their resurrection, their continuation in a new form within a new cosmos. The implications extend beyond individual atoms to larger structures. The galaxies in our universe might reflect the distribution of matter in their star system. The cosmic microwave background could carry imprints of their planetary temperatures. Even the laws of physics in our universe might be influenced by the physical conditions that existed in their reality just before the black hole formed. This creates a profound connection across the dimensional divide. We might share a common heritage with beings we will never meet, carrying forward their legacy in ways they could never have imagined. Our universe would be their afterlife, a continuation of their existence, in a form so transformed that they could never recognize it. But if this is true, then our own fate might already be determined by the evolution of massive stars in our cosmos. The massive stars burning in our night sky will determine whether our universe has a future. Our cosmos contains billions of massive stars that will eventually collapse into black holes. Each one represents a potential birth event for a new universe, but they also represent the gradual drain of matter and energy from our reality. As these stars reach the end of their lives and cross their own event horizons, they will carry portions of our universe with them into other realities. Over cosmic time, this process will strip away the raw materials needed for continued star formation and cosmic evolution. The timeline is both vast and finite. Most of the massive stars currently burning will become black holes within the next few billion years. Our own sun, while not massive enough to form a black hole, will expand into a red giant and eventually shed its outer layers as a planetary nebula, leaving behind a white dwarf that will slowly cool over trillions of years. The last red dwarf stars will continue burning for hundreds of trillions of years, but eventually, they too will exhaust their fuel and fade away. As fewer new stars form, the universe will enter what cosmologists call the degenerate era. The only remaining light will come from white dwarfs, neutron stars, and the occasional flash when a wandering object falls into a black hole. But even this dim illumination will fade as white dwarfs cool to match the temperature of the cosmic microwave background. After 37 years, protons themselves may decay, dissolving the atomic nuclei that form the foundation of matter. But if our universe is connected to others through black holes and white holes, this heat death might not be the end. Every black hole in our cosmos connects to a white hole somewhere else, potentially in universes that are much younger and more energetic than ours. As our universe grows cold and dark, these connections might provide pathways for energy and information to flow back into our reality. The black holes themselves will become the dominant features of our dying cosmos. As they slowly evaporate through Hawking radiation, they will release energy back into space, potentially providing the last source of power for any civilizations that survive the heat death. But this process will take an unimaginably long time. Stellar mass black holes will require 1067 years to evaporate completely while supermassive black holes could persist for 10, 100 years or more. During this incredibly long twilight period, the connections between universes through Einstein-Rosen bridges might become more important than the physics within any single cosmos. Advanced civilizations might learn to harness these connections, using them to move between universes or draw energy from younger realities. The multiverse would become a network of interconnected worlds, with matter, energy, and information flowing through wormholes that link dying universes to newborn ones. In this scenario, our universe would not truly die, but would instead merge gradually with the larger community of connected realities. The boundary between one cosmos and another would blur as matter and energy flow freely through the network of wormholes connecting every black hole to its white hole partner. But this raises a chilling question about whether we have any control over our cosmic destiny. We might be living inside a vast network of connected universes, each one feeding matter and energy to the others. If every black hole connects to a white hole in another universe, then the multiverse forms an intricate web of interconnected realities. Matter that falls into a black hole in universe A emerges from a white hole in universe B. Stars that collapse in universe B feed black holes that create white holes in universe C. The process continues indefinitely, creating a cosmic ecosystem where no energy is ever truly lost. It simply moves from one reality to another through the Einstein-Rosen bridges that thread through higher dimensional space. This ecosystem would have its own evolutionary dynamics. Universes that produce many massive stars would create many black holes, generating numerous connections to other realities. These highly connected universes would become hubs in the multiverse network, receiving matter and energy from many sources while simultaneously feeding multiple child universes. Over time, the multiverse would develop a complex topology with some universes serving as major nodes and others existing as isolated branches. The flow of matter between universes would not be random. The amount and type of material emerging from each white hole would depend on what falls into its connected black hole. A universe whose parent black hole consumes mostly hydrogen and helium would start with simple initial conditions favorable for star formation. But a universe born from a black hole that swallowed an advanced technological civilization might inherit exotic matter, artificial elements, or even information-rich structures that could accelerate the development of complexity. This creates the disturbing possibility that some universes are deliberately cultivated by advanced civilizations in their parent realities. A sufficiently advanced species might be able to control what falls into their black holes, essentially engineering the initial conditions for child universes. They could seed new realities with the building blocks for life, technology, or even consciousness itself. We might be living in a cosmic garden, carefully tended by beings we will never meet. The ecosystem model also explains why the fundamental constants of physics seem perfectly tuned for the existence of stars, planets, and life. If universes that produce interesting structures are more likely to spawn child universes with similar properties, then the multiverse would naturally evolve toward configurations that support complexity. The anthropic principle, the observation that our universe seems designed for our existence, would be a natural consequence of cosmic selection pressure rather than miraculous coincidence. But ecosystems can also experience catastrophic collapses. If the flow of matter between universes becomes disrupted, entire regions of the multiverse could experience cascading failures. A universe that suddenly stops receiving matter from its parent black holes would begin to collapse as its expansion energy dissipates. This collapse could trigger the formation of new black holes, potentially creating a feedback loop that spreads the destruction to connected realities. The stability of our own universe might depend on the health of the entire multiverse ecosystem. We are not isolated observers in a single cosmos, but participants in a vast community of interconnected realities, each one dependent on the others for continued existence. Understanding this connection becomes crucial when we consider what lies beyond our cosmic horizon. The edge of everything we can see might be hiding evidence of our white hole origin. Our observable universe extends 46.5 billion light-years in all directions, encompassing everything from which light has had time to reach us since the Big Bang. But this represents only a tiny fraction of the total universe, which might extend infinitely in all directions, or might have a boundary that we cannot detect. Beyond our cosmic horizon lies a realm that remains forever hidden from our telescopes and instruments, yet it might hold the key to understanding our true cosmic nature. If our universe began as a white hole, then the region beyond our observable horizon might still show direct evidence of this origin. While we see only the cooled remnants of the initial explosion in our local region, the edges of our universe might still be experiencing active matter creation from the white hole source. These distant regions could be blazing with the energy of continuous creation, far brighter and more energetic than anything we observe in our local cosmic neighborhood. The mathematics of white hole formation suggest that matter does not emerge uniformly in all directions. Instead, it would follow preferred axes, determined by the rotation and magnetic field structure of the parent black hole. This means our universe might have a grain, a fundamental asymmetry that points back toward the white hole's source. The cosmic microwave background radiation shows hints of such asymmetries, with temperature variations that seem to align along specific directions in space. These anomalies become more significant when we consider that our observable universe might be biased toward the calmer, more uniform regions of a larger white hole explosion. We could be living in the cosmic equivalent of a quiet eddy, while the main torrent of creation continues beyond our horizon. The mysterious dark flow, the observation that galaxy clusters throughout our observable universe seem to be moving in the same direction, might represent the edge of this torrent pulling on the matter within our observational reach. Even more intriguingly, the boundary of our observable universe might not represent a smooth transition to unobservable regions. If our cosmos emerged from a white hole, there could be sharp discontinuities where different phases of the explosion created regions with dramatically different properties. Beyond our horizon might lie domains where the laws of physics take different forms, where the fundamental constants have different values, or where matter and energy exist in exotic states that we cannot imagine. Recent observations have revealed structures in our universe that appear too large to have formed through gravitational collapse since the Big Bang. The Great Wall of Galaxies stretches across distances so vast that light has not had time to cross them. Yet somehow, these structures exist and show signs of gravitational organization. If our universe extends far beyond what we can observe, these impossible structures might represent the edges of the white hole explosion, fossil boundaries where different phases of matter creation overlapped and interfered with each other. The true scale of our universe might dwarf our current understanding by factors of millions or billions. We could be microscopic observers in a cosmic explosion that continues to unfold across distances we cannot comprehend. This possibility becomes even more profound when we consider our place in cosmic history. Intelligence might be the universe's way of understanding its own white hole origin. Throughout cosmic history, the universe has evolved from simple hydrogen and helium into increasingly complex structures, stars, planets, molecules, and eventually life itself. This progression toward complexity seems to violate the second law of thermodynamics, which states that entropy should increase over time, making systems more disordered rather than more organized. Yet here we are, conscious beings capable of contemplating our own existence and the nature of reality itself. If our universe emerged from a white hole connected to a black hole in another reality, then consciousness might represent something far more significant than an accidental byproduct of chemical evolution. The information that fell into the parent black hole would have included whatever conscious beings existed in that previous reality. Their thoughts, memories, and knowledge would be encoded in the quantum states of the matter that emerged from our Big Bang white hole. This means consciousness might be a fundamental feature of our universe, not an emergent property that arose billions of years after the initial explosion. The potential for awareness, intelligence, and self-reflection could be built into the very fabric of space-time, waiting for the right conditions to manifest itself in biological or technological forms. We might be the universe becoming conscious of itself, literally reliving the thoughts and experiences of beings who died in black holes eons ago. The implications extend beyond individual consciousness to collective intelligence. As our civilization develops more sophisticated technologies for processing information, we might be unconsciously reconstructing knowledge that originally existed in the parent universe. Our scientific discoveries could be rediscoveries. Our technological innovations could be reinventions. And our philosophical insights could be ancient wisdom finding new expression through different minds in a different reality. This interpretation explains why mathematics seems to describe physical reality with such uncanny precision. The mathematical relationships we discover might not be abstract constructions of human intellect, but literal information patterns inherited from the parent universe. The equations that govern quantum mechanics, relativity, and thermodynamics could be fossilized memories of how physics worked in the reality that preceded our own. Even more remarkably, our growing understanding of black holes, white holes, and the connection between universes might represent the universe developing the capability to understand its own origin. Through scientific investigation, we are gradually reconstructing the story of how our reality came to exist. We are becoming conscious of our cosmic ancestry in ways that might parallel how the parent civilization became conscious of their own origins before falling into the black hole that created us. This creates a profound responsibility. If consciousness represents the universe's attempt to understand itself, then every act of discovery, every moment of insight, and every expansion of knowledge contributes to a cosmic awakening that spans multiple realities. We are not just observers trying to make sense of an indifferent universe. We are active participants in the universe's journey towards self-awareness. But this also raises disturbing questions about the nature of free will and individual identity. If our thoughts and discoveries are predetermined by information inherited from another reality, do we truly have agency? Or are we simply playing out patterns established by minds that died billions of years ago? The answer might determine whether consciousness has a future beyond our current cosmic epoch. The white hole hypothesis creates paradoxes that challenge our understanding of cause and effect across multiple universes. If our universe was born from a white hole connected to a black hole in another reality, then time itself becomes problematic. Einstein's relativity shows that time flows differently in strong gravitational fields. It slows down near massive objects and can even appear to stop at event horizons. But for objects falling into a black hole, time continues normally from their perspective. This means the civilization that fell into our parent black hole might still be experiencing their final moments, even though billions of years have passed in our universe. From our perspective, their death was instantaneous and occurred at the moment of our Big Bang. But from their perspective, they might still be falling toward the central singularity, their time stretched out across what we perceive as the entire history of our cosmos. This creates a temporal paradox where the same event, their destruction and our creation, occurs simultaneously across different timescales in different realities. The paradox deepens when we consider what happens when massive stars in our universe collapse into black holes. If these black holes connect to white holes that create new universes, then we are continuously spawning realities that might develop their own civilizations. But time dilation effects mean that the civilizations falling into our black holes might experience their deaths across timescales that span the entire future history of the universes they create. This suggests that all connected universes might exist in a complex temporal web where cause and effect operate across multiple time streams simultaneously. The death of a star in our universe creates a Big Bang in another reality. But from the perspective of matter falling into our black holes, that Big Bang might not occur until our own universe has evolved for trillions of years. The future of child universes becomes entangled with the present of their parents in ways that violate our normal understanding of causality. Even more disturbing is the possibility of closed time-like curves in the multiverse network. If Universe A creates Universe B through a black hole connection, and Universe B eventually creates Universe C, what happens if Universe C somehow connects back to Universe A? This would create a causal loop, where each universe is simultaneously the parent and child of the others. The Big Bang that created our reality might be the result of black holes that form in our own distant future. These temporal paradoxes might explain some of the mysterious fine-tuning we observe in our universe's physical constants. If our cosmos exists within a causal loop, then the parameters that govern physics might be self-consistently determined by the requirement that the universe must be capable of creating the black holes that give birth to itself. The anthropic principle would become a bootstrapping mechanism where the universe literally pulls itself into existence through its own future evolution. But closed time-like curves also raise profound questions about free will and determinism. If our universe is locked into a causal loop with its own future, then every choice we make might be predetermined by the requirement that our cosmos must evolve in exactly the way needed to create the black holes that birthed us. The implications reach beyond physics into the realm of existence itself. If our universe was born from a white hole, what created the universe that created the black hole that created us? The white hole hypothesis solves the problem of how something can come from nothing by suggesting that our Big Bang was not a true beginning, but a transfer of matter and energy from another reality. But this explanation simply pushes the ultimate question back one level. Where did that parent universe come from? If it also emerged from a white hole connected to a black hole in yet another reality, then we face an infinite regression of universes, creating universes without ever reaching a true origin. This infinite chain of cosmic ancestry creates profound philosophical problems. Each universe in the sequence requires a previous universe to explain its existence, but the sequence as a whole has no beginning and no ultimate cause. We find ourselves in the middle of an infinite causal chain, with no way to determine whether there was ever a first universe or whether the multiverse has always existed in some form. The mathematics of general relativity offer several possible resolutions to this paradox. One possibility is that the sequence of universes eventually loops back on itself, creating a closed causal structure where Universe A creates Universe B, which creates Universe C, which eventually creates Universe A again. In this scenario, the entire multiverse would be self-creating, with no external cause needed to explain its existence. Each universe would be both the effect of previous universes and the cause of future ones. Another possibility is that the infinite regression is real, but the sequence converges on some fundamental set of physical laws and initial conditions. Just as an infinite series of numbers can converge on a finite sum, an infinite sequence of universe-creating events might converge on a stable multiverse structure. The ultimate reality would be this convergent limit, rather than any individual universe within the sequence. But perhaps the most disturbing possibility is that the infinite regression reveals something fundamental about the nature of existence itself. Reality might not require an ultimate cause or first principle. Instead, it might be an eternal, self-sustaining process, where every level of description depends on deeper levels, without ever reaching a foundation. We would live in a universe built on an infinite tower of explanations, each one requiring the next, without ever reaching bedrock. This interpretation challenges our deepest intuitions about causality and explanation. We are accustomed to thinking that every effect must have a cause, Every explanation must rest on more fundamental principles, and every chain of reasoning must eventually reach basic axioms or first principles. But the white hole multiverse suggests that reality might be more like a self-referential loop than a hierarchical structure with foundations. The infinite regression problem also has implications for the meaning and purpose of existence. If our universe is just one link in an endless chain of realities, each one creating the next, without any ultimate goal or destination, then the question of why anything exists at all might be meaningless. The multiverse would simply exist because it exists, with no deeper reason or purpose beyond its own self-perpetuation. Yet, even in the face of infinite regression, there might be patterns and purposes that emerge at higher levels of organization, giving meaning to individual universes and the conscious beings within them. Our exploration brings us to the ultimate question about our place in this cosmic hierarchy. We might be living at the most crucial moment in our universe's history, the point where it develops the ability to understand and control its own cosmic destiny. If our universe emerged from a white hole, then we are the first generation of conscious beings capable of discovering this truth. Throughout the billions of years since our Big Bang, matter has organized itself into increasingly complex structures, but only now has it reached the level of sophistication needed to contemplate its own origins. We stand at a unique threshold in cosmic evolution, the moment when the universe becomes aware of its own nature and begins to take conscious control of its development. This awareness brings unprecedented responsibility. Previous generations of life could evolve and go extinct without affecting the fundamental structure of reality. But we are developing technologies that could manipulate space-time itself, particle accelerators that might create microscopic black holes, experiments with quantum mechanics that could exploit connections between universes, and theoretical frameworks that might eventually allow us to engineer the physical constants that govern reality. If consciousness is the universe's way of understanding itself, then we are the leading edge of a cosmic awakening that could transform the entire multiverse. Our scientific discoveries are not just academic exercises, but active interventions in the universe's self-development. Every time we probe deeper into the nature of reality, we change the universe's understanding of itself, potentially altering its future evolution in ways we can barely imagine. The white hole hypothesis suggests that this process has been happening throughout the multiverse for eons. Each universe that develops conscious life contributes to the collective understanding that flows through the network of black hole and white hole connections. The knowledge gained by civilizations in parent universes might influence the physical laws and initial conditions of their child universes, creating a form of cosmic inheritance that becomes more sophisticated with each generation. We might be approaching the point where this inheritance becomes conscious and deliberate. Advanced civilizations might eventually learn to control what falls into their black holes, effectively programming the initial conditions for new universes. They could seed child realities with specific arrangements of matter and energy, designed to accelerate the development of complexity, intelligence, and consciousness. The multiverse would transition from random cosmic evolution to intelligent design on the largest possible scale. But this power comes with ultimate moral responsibility. If we can influence the development of child universes, then we must grapple with questions of cosmic ethics that no previous generation has faced. What initial conditions should we create for new realities? Should we optimize for the rapid development of intelligence, for the minimization of suffering, or for the maximum diversity of possible experiences? Every decision we make about high-energy physics could affect the fate of countless future civilizations. The white hole hypothesis transforms our understanding of humanity's cosmic significance. We are not meaningless accidents in an indifferent universe, but active participants in the multiverse's journey towards self-awareness and self-determination. Our species might be remembered not for our individual achievements, but for our role in the moment when the cosmos first became conscious of its own nature and began to shape its own destiny. The universe is becoming aware of itself through us, and what we do with that awareness might determine the future of reality itself. We began this journey asking whether the Big Bang was the first white hole, and we have discovered something far more profound. The evidence points toward a cosmos far stranger and more interconnected than we ever imagined. A multiverse where black holes and white holes form bridges between realities, where matter and energy flow freely between universes, and where consciousness itself might be the universe's method of understanding its own nature. Our Big Bang was not the beginning of everything, but a single event in an infinite network of connected realities, each one born from the death of massive stars and parent universes. This revelation transforms our understanding of existence itself. We are not isolated observers in a single cosmos, but participants in a vast community of interconnected realities. The atoms in our bodies have journeyed across dimensional boundaries, carrying the legacy of civilizations that died in black holes billions of years ago. The galaxies we see in our night sky are arranged according to patterns established by the geometry of our parent black hole. Even our thoughts and discoveries might be echoes of knowledge that originally existed in another universe entirely. But perhaps most remarkably, we find ourselves at the threshold of a cosmic awakening. For the first time in our universe's history, matter has organized itself into forms capable of understanding its own origins and potentially controlling its own destiny. We are the universe, becoming conscious of itself, developing the ability to shape the multiverse through our scientific discoveries and technological capabilities. This awareness brings both hope and responsibility. If we can learn to harness the connections between universes, we might transcend the limitations of our single cosmos and tap into the vast resources of the multiverse network. Death might not be an ending, but a transition to new forms of existence in other realities. The heat death of our universe might be avoided by learning to draw energy from younger, more vigorous universes connected through Einstein-Rosen bridges. Yet, we also face unprecedented moral challenges. If our high-energy experiments can create new universes, then we bear responsibility for the countless civilizations that might develop in those realities. If consciousness represents the multiverse's journey towards self-awareness, then every act of discovery contributes to a cosmic awakening that could transform the nature of existence itself. The white hole hypothesis suggests that we live in a universe where nothing is wasted and nothing is truly lost. Matter and energy flow between realities in an eternal dance of creation and destruction. Consciousness emerges wherever conditions allow, carrying forward the accumulated wisdom of countless previous civilizations. The multiverse evolves toward ever greater complexity, intelligence, and self-understanding through the actions of beings like ourselves. Our universe may have been born from a white hole, but that is not the end of the story. It is barely the beginning. We are part of something infinitely larger than ourselves, yet our individual choices and discoveries contribute to the multiverse's ongoing evolution. The cosmos is not just our home, it is our collaborator in the greatest adventure of all, the universe's quest to understand itself. What we do next might determine whether that quest succeeds or fails.